London, 1925. A British zoologist named Guy Coburn Robson, working at the Natural History Museum, is examining two objects that have just arrived from Antarctic waters. They came from the stomach of a commercially hunted sperm whale. Two arm crowns, the proximal portions of a squid's arms, still bearing their distinctive swiveling hooks. In cephalopod anatomy, arms and tentacles are distinct structures. These were arms. Robson had never seen anything like them. From these fragments, no body, no complete specimen, no observation of a living animal at any stage, he named a new species. Mesonychoteuthis hamiltoni, the colossal squid. His formal description was published that year in the Annals and Magazine of Natural History, and the two arm crowns went into storage in London, where they remain today as the species type specimens, the physical objects that define its existence in scientific classification. That was humanity's entire introduction to the heaviest living invertebrate on Earth. For the next several decades, every new piece of knowledge about this animal came from the same source: other sperm whale stomachs. A beak here, another pair of arm crowns there. Researchers picked through preserved gastric contents in laboratories around the world, while the animal itself remained entirely invisible. By the mid-20th century, scientists had reached a quiet consensus. M. hamiltoni must be one of the rarest animals on Earth. The evidence was vanishingly scarce. Te Papa Tongarewa, New Zealand's national museum, which would eventually house some of the finest specimens in existence, noted in their review that only around 8 adult individuals had been reported, and all but 2 of those came from sperm whale stomachs. 8 adults. A century of inadvertent encounters. A species known entirely from digested remains. The obvious conclusions seemed almost inescapable. Whatever was down there wasn't much. They were wrong, and the proof had been sitting in their beak jars the entire time. The man who decoded it was Malcolm Roy Clark, a British marine scientist who spent decades collecting cephalopod beaks from sperm whale stomachs across the southern hemisphere. Clark thrived. His contribution was patience and a methodology that seems obvious in retrospect. Collecting cephalopod beaks, the hard, parrot-like mouthparts that survive digestion long after surrounding tissue dissolves, from sperm whale stomachs across the southern hemisphere, identifying each beak to species and converting its dimensions to a body mass estimate using empirical allometric equations. He did this across hundreds of whales, over years, aboard multiple research vessels. He accumulated samples at every opportunity. Clark didn't seem bothered. He had data to compile. His 1980 discovery report, Cephalopoda in the Diet of Sperm Whales of the Southern Hemisphere and Their Bearing on Sperm Whale Biology, became the foundational text for everything that followed. The finding that emerged from it was deeply strange. Mesonychoteuthis hamiltoni beaks appeared in approximately 14% of all squid beaks found in Antarctic sperm whale stomachs by count. 14% doesn't sound exceptional, but because the colossal squid is so much larger than most of the other prey items sharing stomach space with it, that 14% of beaks translates, through the allometric equations, to roughly 77% of the total squid biomass those whales were consuming. 3/4 of the caloric intake of an entire whale population, by weight, coming from one species. Te Papa states it plainly. Scientists consider M. hamiltoni to be a major prey item of sperm whales in the Southern Ocean. Beaks comprise 14% of the numbers found in sperm whale stomachs from the Antarctic, and, because of the large size of the species, this represents an estimated 77% of the biomass consumed. Some sources round this to 80%. Either way, the arithmetic leads somewhere absurd.
The rarest animal on Earth is apparently the main course for an entire whale population. To be precise about the figure, it's an estimate, derived indirectly from beak dimensions converted to body mass, not from weighed flesh. It applies specifically to large adult male sperm whales feeding in Antarctic waters, not to global sperm whale populations. In other regions, the Galapagos, the Mediterranean, diet profiles look quite different. But in the Southern Ocean, whale after whale after whale told the same story. A subsequent reanalysis by Sherrill in 2021, examining 131,577 lower beaks from 237 commercially caught whales, found 3 Southern Ocean endemic squids together, accounting for more than 90% of fresh cephalopod prey items in Antarctic whales, with the colossal squid leading the count. That isn't a species on the edge of existence. That is the backbone of one of the ocean's most productive food webs. And the sperm whales had known where to find them for the entire duration of the scientific confusion. They were, after all, the ones who kept delivering the evidence. There's a reasonable argument that attaching passive cameras to individual sperm whales and following their hunting dives would have resolved the question decades earlier. The whales clearly knew the way. So why couldn't any human observer find one alive? It took 56 years after Robson's 1925 description to obtain something that qualified as a complete specimen. In 1981, the Soviet trawler Evrika, operating at approximately 750 meters depth in Antarctic waters near Dronning moored land, brought up a large colossal squid in its nets, inadvertently, per National Geographic's account of the event. The squid happened to be there. The specimen was later identified as an immature female, with a mantle length of approximately 2.42 meters and a total length of around 5.1 meters, roughly 17 feet. It was the first time a reasonably complete body had been recovered directly from the ocean rather than digested out of something else. Stomach contents: 1 trawled corpse, technically still immature, 0 live sightings. The pattern continued for decades. A subadult female caught by a New Zealand longliner in the Ross Sea in 2003, a large individual captured alive on a toothfish longline off South Georgia in 2005 at approximately 1,625 meters. The San aspiring specimen in 2007, the first intact adult male ever recorded, described by Te Papa as the most intact adult colossal squid ever caught, landed while it was holding onto a toothfish the vessel was hauling aboard. Every single specimen was an accident of fishing, not an act of observation. No one had watched one move. No one had filmed one in its environment. As of 2024, Te Papa noted that no comprehensive scientific description of a mature adult male or female colossal squid had yet been prepared, despite specimens being available. The geography compounded everything. The colossal squid appears endemic to the Southern Ocean, circumpolar, from the Antarctic continent up to the subantarctic front, unlike the giant squid, Architeuthis dux, which ranges across temperate and subtropical oceans globally. What that means in practice: the Southern Ocean is arguably the most remote and consistently violent stretch of open water on Earth. Wave heights regularly exceed 10 meters. Wind speeds above 100 kilometers per hour are documented routinely. Water temperatures run near freezing. Operating a deep-sea research vessel there costs tens of thousands of dollars per day, and adults are thought to inhabit depths below 1,000 meters, inferred from sperm whale dive behavior and beak evidence suggesting dives to at least 2,200 meters. The polar environment itself amplifies body size in ways that align with the colossal squid's scale. The same cold water physics that produces the heaviest living invertebrate also generates isopods and amphipods multiple times larger than their shallow water counterparts. Polar gigantism, a documented phenomenon across multiple Southern Ocean taxa. For roughly the first 30 meters, scuba diving is practical. Past that, observation becomes exponentially more expensive and technically demanding. Past 200 meters, you're in the twilight zone, and that's where the story gets considerably broader. Between 200 and 1,000 meters below the ocean surface lies a layer of water that wraps around the entire globe, the mesopelagic zone. Light reaches it, but too dimly for photosynthesis.
Early oceanographers concluded from this and from their sampling data that the zone was biologically sparse, cold, nutrient-limited, and largely empty. They surveyed it and moved on. They were wrong in a way that still reverberates through the field. NOAA Ocean Explorer documents what happened during the Second World War when sonar systems newly installed on naval vessels began returning strange readings. Technicians noticed the seafloor seemed to be much shallower in some areas during the day than at night. The apparent bottom rose by hundreds of meters every evening, then sank before dawn. MBARI, the Monterey Bay Aquarium Research Institute, confirms the same discovery independently. Sonar pulses were bouncing off a false bottom, actually a layer so dense with organisms it reflected sound like rock. It became known as the deep scattering layer. It took years to understand what the sonar was actually hitting. Billions of animals migrating between the mesopelagic zone and the surface waters every single night. NOAA's ocean exploration program describes diel vertical migration as the greatest migration on Earth. A 2025 paper in Nature estimated the biomass in motion exceeds 4 gigatons per kilometer per day, surpassing any other animal migration phenomenon on the planet by total mass. Billions of animals ascending under cover of darkness to feed at the productive surface, retreating to depth before dawn to avoid predators that hunt by sight. Every night, silently. In an ocean layer we had been categorizing as barren. The sonar had been detecting this since the 1940s, and the instruments outran the understanding for decades. In 2014, Irigoyen and colleagues published research in Nature Communications drawing on acoustic data from the Malaspina 2010 Global Circumnavigation Expedition. Their finding on mesopelagic fish biomass between 40 degrees north and south latitude, the previously accepted estimate of approximately 1,000 million tons appeared to be roughly 10 times too low. The revised figure ran between 11,000 and 15,000 million tons. The conversation summarized the implication. The fish biomass in the global ocean has been largely underestimated by at least 10 times and most likely 30 times. Phys.org put the headline simply, 95% of world's fish hide in mesopelagic zone. An ecosystem surveyed for decades, called nearly empty, off by an order of magnitude. The point isn't the specific revision, the point is the pattern. An environment that was actively, repeatedly surveyed by trained oceanographers and systematically underestimated because the measurement tools introduced biases the researchers couldn't fully account for. Nets scared animals away or sampled too coarsely. Submersibles announced their arrival so loudly that the layer thinned as they passed. The 2014 correction wasn't negligent science being fixed. It was the consequence of finally developing approaches sensitive enough to capture what was actually there. If we could be that wrong about an entire mesopelagic ecosystem, one we had been pinging with sonar since the 1940s, then being wrong about one species within that ecosystem isn't surprising. It was predictable. Standard deep-sea ROV operations. A vessel holds position on the surface, engines running. A large robotic platform equipped with powerful white floodlights and multiple electric thrusters descends on a cable. The thrusters generate significant noise. The lights are bright enough to illuminate terrain for camera work. The whole assembly arrives at depth, looking and sounding like nothing that has naturally occurred in that environment for the entire duration of animal evolution. Researchers noticed the behavioral effects relatively early. Spanier, Cobb, and Clancy published a formal study in Marine Ecology Progress series in 1994, examining ROV impacts on American lobsters, among the first systematic analyses of the problem. Their finding, the presence of the ROV in an operational state significantly reduced feeding activities. ROV lights and thruster sounds, presented separately in laboratory conditions, each reduced normal behavior. Combined, they were more effective still at suppressing it. The authors recommended that ROVs used for behavioral research minimize lights and thruster noise. perhaps by using quieter thruster motors and either infrared illumination or low-light cameras. In 1998, a report for the Monterey Bay National Marine Sanctuary documented concerns raised by Richard Parrish about potential damage to visual systems of deep-sea animals following exposure to bright lights on submersible vehicles. By 2024, a University of Rhode Island dissertation by Sappi, titled "Treading Carefully in the Deep Ocean," had compiled new evidence of avoidance behavior in deep scattering layers during scientific ROV transects, the layer itself thinning as the ROV moved through it, and documented the observational biases associated with scientific ROV platforms as real and measurable. Research published in Frontiers in Marine Science noted the systemic bias of the method introduced by ROV illumination, affecting not just what's attracted to camera, but what flees before it arrives. None of this is theoretical for the colossal squid. The animal has the largest eyes of any living creature on Earth. The preserved eye of a colossal squid measures approximately 27 centimeters in diameter, the size of a soccer ball, per Te Papa and Mission Blues reporting. Professor Eric Warrant of Lund University, who participated in the dissection of a colossal squid specimen at Te Papa in 2008, stated, "They are probably the largest eyes that have ever existed." In Current Biology in 2012, Nilsson and colleagues published their analysis. The eyes of giant and colossal deep-sea squid are 27 centimeters in diameter. Modeling suggests that the huge eyes are uniquely suited for spotting sperm whales. The next largest eyes in the animal kingdom, Warrant noted, measure about 9 centimeters, a swordfish's. Below 9 centimeters, the energy cost of building a larger eye outweighs the visual gain for most tasks. The only task for which larger eyes remain justified is detecting large, luminous objects, specifically the bioluminescent wake a sperm whale produces as it pushes through dense populations of planktonic organisms. The eye didn't evolve to find food. It evolved to detect one specific predator at the absolute limit of visible range in near total darkness. As Warrant explained, sperm whales trigger bioluminescence from the great density of tiny planktonic animals that they collide with while swimming. This light creates a bright aura around and behind the whale that can be seen at a great distance in the sea, about 120 meters away, but only by an animal with an eye as large as that of the colossal squid. The squid evolved this eye as an early warning system tuned to the minimum available light in the Southern Ocean, hundreds of meters down. Then we showed up with ROV floodlights. Cephalopods don't have eyelids. There is no mechanism to close against sudden, overwhelming artificial illumination. The eye that evolved to collect every available photon from the faintest bioluminescent trace is now receiving an input it has no physiological history with whatsoever. A research ROV's floodlights in that environment would register something like a stadium searchlight appearing in a room where the maximum expected brightness was starlight. Meanwhile, engine noise from the research vessel above propagates through water far faster than through air, carrying for miles. A standard research operation in the Southern Ocean isn't a stealthy exercise, it's a proclamation. One oceanographer reframed the entire problem with a single question. What if the reason we couldn't see deep-sea animals was because we were looking the wrong way? That was Edith Widder.